All right, let's talk about Python. We all love it, right? The syntax is clean, the ecosystem is huge, it's just a joy to work with. But let's be honest, sometimes, especially when you're doing some heavy lifting, that beautiful Python code can start to feel, well, a little slow. So today, we're going to play doctor. We're going to diagnose what's ailing our Python code and figure out how to make it faster and way more efficient.
But before we write a single prescription, we have to take a kind of doctor's oath. The legendary computer scientist Donald Knuth said it perfectly. Premature optimization is the root of all evil, and that is our #1 rule today. We're not just going to start throwing random cures at our code, hoping something sticks. No way. First, we have to find the actual problem. We have to diagnose before we prescribe.
So, here's our consultation plan. First, we'll get to the bottom of the Python performance problem itself. Then, the most important part, the diagnosis, finding that bottleneck. After that, we'll dive into treatments, starting with smarter code, then moving beyond pure Python, and finally exploring the real advanced stuff, parallelism.
Okay, let's kick things off with Section 1, the Python performance problem. See, to find the cure, you've got to understand the condition. Python is what's called a dynamic language. That means the interpreter is doing a ton of work behind the scenes while your code is running, like figuring out the types of your variables on the fly. Now, that flexibility is awesome, but it comes at a cost. It creates overhead that makes Python naturally slower for really intense, CPU-heavy tasks when you compare it to compiled languages like C.
Now we're at the most critical step, our diagnosis, finding the bottleneck. And the subtitle says it all. It's time to stop guessing and start measuring. You know, a good doctor doesn't just guess what's wrong with you, and a good developer doesn't either. We need to find the real, actual root cause of the slowdown before we even think about trying to fix it.
And here is the mantra that we are going to follow religiously. It's a simple 3-step process. Step 1, make it run. Just get the thing working. Step 2, make it right. Clean up the code, make the design solid. And only then, after it works and it's well designed, do we get to step 3, make it fast.
So, how do we actually do this diagnosis? We use a tool called a profiler. You can think of a profiler as like an MRI for your code. It runs your application and watches it, timing exactly how long your program spends inside every single function. It's the key to finding those resource hogs. And the best part? Python has a great one called cProfile, built right into the standard library. So let's look at our first patient. It's a simple particle simulator. We run it through the profiler and wow, the results are just crystal clear. Look at this chart. There's no guesswork needed here at all. One function, evolve, is eating up a massive 85% of the total runtime. We've found our bottleneck. It's staring us right in the face.
All right, with a clear diagnosis in hand, we can start prescribing our first round of treatment. Welcome to Section 3, Smarter Code, Faster Results. Think of this as Level 1 care. These are the easy fixes, the low-hanging fruit. We're going to focus on building better Python habits, like just choosing the right tool for the job.
And check this out. A seemingly small choice can have a huge performance impact. Let's say you're constantly adding new items to the very beginning of a collection. If you use a standard Python list, that's a really slow operation. It gets slower and slower the bigger the list gets. But if you just swap that out for a dequeue from the collections module, that same operation becomes what we call constant time. It's always fast no matter how big the collection is. It's practically a free performance upgrade.
Here's another powerful technique, memoization. It's a fancy word, but the concept is super simple. It's just caching your results. If you have a function that's slow to run and you keep calling it with the exact same inputs, why do the work all over again? Just store the answer. Python makes this ridiculously easy. There's a one-line decorator called LRU_cache that does all the work for you. It's an amazing way to cut out redundant calculations.
Okay, so better habits are a fantastic start. But what happens when our patient needs more intensive care? Well, that brings us to Section 4, Beyond Pure Python. When performance is absolutely critical, it's time to stop messing around and call in the specialists. And I'm talking about powerhouses like NumPy and Cython.
Let's go back to our particle simulator's evolve function. On the left, you see the original code, with that pure Python for loop just chugging along, one particle at a time. But on the right, that's the NumPy version. Instead of a loop, we're performing a single vectorized operation on the entire array of particles all at once. The code's not just cleaner, it hands off all the heavy lifting to NumPy's super optimized C code. And the result of that one little change? It's about 7 times faster. And here's the really cool part. That advantage grows as your data grows. The more particles you have, the bigger the performance gap becomes between the Python loop and the NumPy version.
But what if 7 times faster still isn't fast enough? Time to call in our next specialist, Cython. Cython is amazing. It lets you add C-style type declarations right into your Python code. So by telling Cython, hey, this RI variable is an array of doubles and I is a C integer, we give it all the information it needs to skip the Python interpreter entirely and compile this function directly into crazy fast C code.
So what's the result of bringing in this super specialist? The performance jump is just staggering. We are now looking at a speedup of roughly 30 times compared to our original Python code. Just think about that for a second. We've got code running at nearly the speed of C, but we didn't have to leave the comfort of our Python syntax.
Okay, so our code is now incredibly fast on a single CPU core. But what if one core just isn't going to cut it? Well, that brings us to our final section, the next frontier. For the toughest performance problems, we need the most advanced therapy of all, parallelism.
Now, before we can talk about parallelism in Python, we have to talk about the elephant in the room, the Global Interpreter Lock, or the GIL. The GIL is basically a rule in the main Python interpreter that says only one thread can actually be running Python code at any given time. This means for tasks that are heavy on the CPU, standard Python threads can't give you true parallel speedups on multiple cores.
So how do we get around this GIL problem? The answer is to use processes instead of threads. See, threads are lightweight and they share memory, which is great for things like waiting for network requests. But processes, they each get their very own memory space and their own Python interpreter. They completely sidestep the GIL. And that makes them the perfect tool for doing heavy-duty parallel work on the CPU.
So that leads to the big question. When should you actually reach for Python's multiprocessing module? Well, it's perfect for problems that are what we call embarrassingly parallel. Basically, any task that you can easily break up into totally independent chunks. Think about our particle simulator again. How one particle moves doesn't depend on another. As long as the time it takes to do the work is more than the time it takes to send the data to a new process, multiprocessing is your ticket to using every single core your computer has.
So when you put it all together, we've basically built what I like to call the ladder of optimization. It's our entire treatment plan. You always start at the bottom with smart, clean Python code. Then you use a profiler to find the real problem. Only then do you start climbing the ladder as needed. You vectorize with NumPy, you compile with Cython, and for the absolute toughest jobs, you go fully parallel. You don't jump straight to the top. It's a systematic climb.
So, what's the big takeaway from our consultation today? It's that getting high-performance Python isn't some kind of dark art or magic trick. It's an engineering discipline. It's about being systematic, about finding the weak spots, and then methodically choosing the right treatment for that specific problem.
We've just armed you with a full doctor's bag of tools for diagnosing and treating Python performance issues. So the only question left is, what piece of slow code in your own projects are you going to go heal first? Thanks for tuning in.